Hi math students, we're back just revisiting this first example, example A, where it looked like we had this highest common factor of 8xy to the power of 4, which we pulled out the front and we had remaining in brackets as x squared minus 2y squared. And then I went on to say, look, it can be further factorized to give these bracketed factors that we see over here. So this is just a quick rundown on how that process works. And to look at it, we kind of need to revisit this concept called surds. And we've touched on this previously. Just as a recap, a surd is an irrational number that has to be written as a rounded value when we actually evaluate it. So what we do is we keep that number in root form to keep its exact value accurate. So in other words, when we want to keep using the number in an operation to make sure that our answer is accurate, we'll use the root form. So for example, if I have the square root of 4, that's definitely not a surd because we can evaluate that to an exact value of 2. However, if I have square root of 3, that is a surd, mainly because when I evaluate that, I get a decimal answer that has no obvious pattern and it goes on infinitely. And when we have to write this number down from our calculators, for example, we would have to write down a rounded version of the answer. So you might like cut it off at 2 decimal places, but the answer you're writing down is approximate because it's a rounded answer. So if we want to use the exact value of it, we'll keep it in surd form. Okay, so surds are really useful, and in this case, they're useful to us when we want to further factorize a quadratic like this, which we can see might be a difference of 2 squares, but the problem is that one of the numbers is a square number. Well, it's not a number, it's a letter. X squared is a squared version, but the other side is not a square number. So this is where surds come in to help us further factorize. So let's get into it and have a look at some of these examples on how we further factorize these expressions using surds and difference of 2 squares pattern. Alright, let's get this first example. We've got x squared minus 11. Now I said we've got to use this difference of 2 squares pattern. So if I try and match up what these are, I could say that the a squared's representing the x squared and the 11's representing the b squared. And then looking at them separately, just as a bit of side working here, if I know a squared is equivalent to x squared, that means the singular, a, is going to be the square root of x squared, which is just x. And the same with b. If I know b squared is representing 11, then that means b by itself is going to be the square root of 11. Alright, so then popping that back into our thinking here of trying to apply that difference of 2 squares pattern to factorize, the steps that might be helpful is you acknowledging, look, that could be x squared minus the fact that I've got the square root of 11 squared. Okay, so thinking about it, if I take the square of the square root of 11, I just end up with 11. So I haven't actually changed anything there. I've just put it in a more useful form. So now I can just go ahead and apply my difference of 2 squares pattern and go, look, I know that's going to factorize into the first number plus the second, and then the negative version of the same thing. And what we've actually done is we've further factorized this x squared minus 11 into a usable form, which is actually very useful when it comes to solving quadratic equations, what we'll look at in a further video. Alright, your turn now. Have a go at example B here and see if you can further factorize this quadratic. Press pause and give it a crack. Okay, hopefully you came out with this as your solution. So just talking through it, we know that it's going to be in this difference of two squares pattern, so it's going to factorize like this. We can identify that the a squared is the x squared, the b squared is represented by the 7. So if we pull it apart and find the singular of each, we can see that that will can be converted into x squared minus the square root of 7 all squared, which we know will factorize into these bracketed forms after I apply that difference of two squares pattern. And just remember that either version is acceptable, because when you think about it, when two numbers are multiplied, or in this case two expressions are multiplied, it doesn't matter the order, you'll get the same result. Okay, we're going to have a look down here at a more complicated example. Now, with C, we're seeing that one of the terms is a bracketed term that's been squared. And honestly, this is no different to the others. It's just a bigger square number, if you want to think of it like that. So if I pull it apart like I did previously, I can see that the x minus 2 squared represents the a squared. So singular, I can see that a is just going to be x minus 2, and we'll just keep it bracketed so we know that it's all together. And we know that the b squared is our 7, so that means the singular b must be the square root of 7. So then applying our difference of two squares, we do know that that's x minus 2 all squared, okay, minus the square root of 7 all squared, and popping it now into that difference of two squared pattern, all factorized, we've got our a part, the x minus 2, plus square root of 7, and the negative version of it. Okay, and that's factorized. Now you might want to pop away the brackets there, and you can write it like this as well. Okay, have a go at D. Press pause and see if you can do that one by yourselves. Be back in a sec. Just checking in. So hopefully you pulled it apart like this, where you recognize that maybe the a squared bit is associated with the x plus 5 all squared, therefore singular, your a is x plus 5. Pulling apart the b squared, we know that's represented by the 13, so b singular must be the square root of 13. Popping it into that pattern, we end up with the factorized version. So this here, I've got the a minus b part, and I've got the a plus b part, and then all I've done in the final bit is to get rid of those little brackets so it looks a bit cleaner, and this is your further factorized version of that initial expression. Okay, I have one more example to run through with you. Try E. It's just like an easier type simplifying algebraic expression question, where you've just got to apply this further factorization of the top bit and see how it pans out with any possible cancelling. So press pause, see if you can give it a go, and we'll check back in shortly. Alrighty, so this top bit, hopefully you're looking at it and going, look, oh, I think that's in that difference of two squares format. The first x minus 5 all squared is your a squared. It's terrible too. And then this 3 is the b squared bit. So again, if you wanted to do the side thinking, if we know our a squared is the x minus 5 all squared, then the singular must be just the x minus 5 by itself. B squared is our 3, so b singular is going to be our square root 3. So I could go straight away to my fully factorized version. I won't jump steps though. So we've got our x, not to the power of 5, x squared minus our square root 3 squared all over the bottom bit there, which we can't factorize at all. Putting it into its difference of 2 squared factorized form, I can see that what I end up with is coincidentally something that I already have on the bottom. So if I consider that denominator will cancel out with part of the factor I have in the numerator, I should be able to see that this simplifies to x minus 5 minus square root of 3. How did you go? Okay, hopefully you get a bit of confidence about further factorizing these expressions that kind of look like they're a difference of 2 squares. You just have to manipulate one of the terms to fit that pattern, and then, like I said, it's very useful for when we start solving quadratic expressions, which will be in a further video. All right, good luck practicing questions.